Welcome, everyone. Good afternoon. With great pleasure, I welcome Francoise Combes from the Observatoire de Paris, who will be talking to us about molecular gas fueling and feedback in nearby active galactic nuclei. This is the last talk of this semester, so it is great that so many of you could come. Let me say a few words about the speaker. Francoise studied in Paris at the ENS and Paris 6, as I understand. Then she moved to the Observatoire, and you have been there ever since. That really tells you Paris is a beautiful city, and people who once have been there will never move away. I can fully understand it. She has been in many committees and in many important functions in astronomy in France. At the moment, she is a secretary at the Assembly of Professors of the Collège de France. And she has had many other important functions in the International Astronomical Union and so on. So I should not take away this valuable time. Let us welcome Francoise. And
thank you very much. I'm very happy to be there. So indeed, I will speak about molecular gas fueling and AGN, and the outline of my talk would be first some fundamentals, recalls about what is a galactic disk and how we drive the gas to the center, drive the matter to the center because of angular momentum transfer. I will, of course, talk about the dynamical, non-axisymmetric feature like bars and spirals. And then once you have fueled your AGN by gravity torques, then you have a feedback. The AGN is giving back the energy. So either it is a very strong AGN and it is galactic winds, or it is a very low energy AGN and it is by radio mode, the radio jets. I will describe some evidence, and I will describe recent work where we have a high resolution with ALMA, and we have discovered a lot of molecular tori, or nuclear disk decoupled, and this may be the key of the unification. As you know, the Seyfert 2 are obscured, Seyfert 1, at least some part of them, not all. And I will try to show you that in general the nuclear disks are completely decoupled. They have random orientations to the disks. So why first we need angular momentum transfer? In fact, the gas, here you see a disk hadron, but you can consider a disk of galaxy like an accretion disk, in fact, and the gas wants to go to the center to have the minimum energy, so you want to minimize energy, but of course, like an accretion disk, you have a lot of rotation, angular momentum to get rid of, and this you can compute at the scale of kiloparsec scale. The viscous torques due to the gas are negligible. This was a computation made 20 or 30 years ago by Lin and Pringle and Lindenberg and so on. And those, what replaces viscosity at these scales is like gravitational viscosity, in quote, because the gas is unstable with respect to the Toomre criterion. It can make spirals, bars, and so on. And these instabilities make that there is non-axisymmetry. So you have a tangential force. When it is axisymmetric, you have only radial force, so no torque. When you have non-axisymmetry, you have a tangential force, torques, and then you can exchange angular momentum. And if we could, viscosity is to exchange angular momentum. There is some viscosity with self-gravity, and then you a small amount of gas is taking all the angular momentum away, and to allow all the gas to fall to the center to have this minimum energy. So this is the principle. Now, how it is done in practice in spiral or bar galaxies, you know that 2/3 of galaxies are barred, so it's a most normal, regular morphology, the bar galaxy. And the bar galaxy, it's known also for a long time that the orbits of stars, Kontopoulos, for instance, in the 80s, 30 years ago or more, they have established that the orbits of stars are trapped around periodic orbits, and these periodic orbits are either parallel to the bar. For instance, there is a bar horizontal here. So the first one are X1 orbits which are parallel to the bar, and then each resonance. A resonance means that you have the bar is rotating at a constant speed, which is in general smaller than the omega angular speed of the stars, and then it has a very low angular momentum, and then you have a co-rotation. You have also Lindblad resonances when you have rational ratios between omega and kappa, which is the epicyclic frequency. So all these, each resonance, you can have an outer Lindblad resonance and so on. I don't enter into the details. The main point here is that you turn the orientation of the periodic orbits by 90 degrees at each resonance. This you have just to, the bottom line is that. And of course, these are for stars, because stars are not colliding to each other, are not dissipative, they don't see each other, so they can be perpendicular. But when you have gas, of course, it tends to follow these orbits, but then they are entering into collision, they are dissipative, and then after having parallel, they must go from parallel to perpendicular, and this occurs by successive collisions. So you can imagine that they are tilted here by a regular amount, and the precessing of these orbits, the precessing rate of these orbits is, as I will tell you a little later, omega minus kappa over 2, kappa being the epicyclic frequency. So you see that the gas will have this morphology, and it is like the Kalnash orbits, and you see how you can have a spiral structure, even if the bar in the stars have no spiral structure, you can have a spiral structure in the gas because of this collision and dissipation rate of the gas and this orientation by 90 degrees. So this makes a spiral structure. And of course, since the gas is not in phase with the stars, you will have a torque from the stars to the gas to realign it. And this is a gravity torque from the old stars to the gas, which will bring the gas to the center. So in fact, what happens is that you have this kind of curves here. Omega is V over R, the circular orbit over the radius. And then you can compute omega minus kappa over 2, kappa being the epicyclic frequency, and omega plus. So this can define the inner Lindblad resonance when you have the velocity of the bar, pattern speed of the bar equal to omega minus kappa over 2. And then what happens is that the bar exerts a torque on the gas, and we will see that the sign in side rotation is negative, and all the gas is piling up at the ILR, which is a ring, and we'll see some example of rings. And of course, it's not in the goal to fuel the AGN, because the gas is piled up here, it's stored there, and you cannot fuel the AGN. What happens, you have to wait, in fact, that after a while the gas is making its way to the center and the mass is increasing. And all these curves are increasing a lot. Omega minus kappa over 2 is increasing with the mass, with the velocity and so on. And after a while, the precessing rate here, omega minus kappa over 2 in the center, is too fast to be synchronized with the same rate in the outer parts. And you cannot have a constant pattern speed, and you have a second one, which is decoupling. And you see here in simulations, stars, a big bar and a small bar, and the gas also. So it's a way that you can decouple a nuclear bar inside the big bar, because there is too much discrepancy between the two precessing rate, and it cannot be synchronized by self-gravity. So this is the way that you can fuel the AGN, because at some point, transiently, you can store the gas in the ring, and after a while, when there is enough mass, you can have an embedded structure that will prolong the action of the bar towards the center. And of course, you can have one, you can have several, and one is also favored or fostered by the fact that inside here you can have two ILRs, and inside the two ILR you have perpendicular orbits, and the perpendicular orbits destroy the bar because they are perpendicular to the bar, and also you have a vertical resonance that weaken the bar. So the center, it's weakened. So if I summarize the signs, it's quite easy, intuitive to see what will be the sign of the gravity torques. In fact, here you have the bar, which is a potential which is parallel to the OX axis, horizontal, and the co-rotation is there. The bar is inside this co-rotation. Outside, the orbits are perpendicular, so it doesn't support the bar. And we have shown that since omega minus kappa over 2 were always falling here, so if you come from the outside and you come in by dissipation, you will always precess faster. Okay, so here you precess faster, and that's why all the orbits of the gas are crowding here. So outside, if omega is the sign of rotation of the galaxy, you have the spiral structure here, and you can at once see that the tangential force is restoring the particles to the bottom of the potential wall, which is here. So you have a positive torque. Positive because it goes at the same sense as omega. So what does it mean? It does mean that all the gas from here to here will be driven out and not in. So this is why you find some outer, I think there was an example here, yes, barred galaxies where you can have 3 rings. These 3 rings are better seen in the B minus V color because star formation in the ring. Here is an inner ring, nuclear ring, and outer ring. So outside rotation, you push all the gas to the outer ring. And when the gas is in a ring, it is symmetrical with respect to the bar, and it is no torque at all. So you can stall there. So here you see why it is positive. And then if you want to see, of course, here you will have symmetrically torque, which is negative here. Just going back to but there is not a maximum of gas here. The gas is piling up here, so this is winning. If the gas had a symmetric distribution, the torque would be 0 in average. So inside the co-rotation, then again, omega minus kappa over 2 means that it is processing more rapidly, it is leading, so you have this leading thing here, and you see at once why it changed the torques, because now you are in the quadrant. You see here there's 4 quadrants. These 2 quadrants are positive, these 2 quadrants are negative for the torque. So here you are in the 2 quadrants that you had not before. So you are in negative quadrants. So the tangential force is this, and now you have a negative torque. And then all the gas inside co-rotation to the ILR is coming in. So you are indeed driving all the gas to the ring, which is quite easy to see. And that's why we have done. In fact, we wanted to know at which rate you can fuel an AGN, and we have tried to have the potential. How you can have the potential? You can have, in general, the potential in these spiral galaxies at the kiloparsec scale is not due to the dark matter. The dark matter is in the outer parts. So you can neglect the dark matter, and you have mainly the old stars. So you take a near-infrared image of the old stars, you deproject to have a face-on galaxy, and then you can compute from the surface density of stars the potential. And then you can also have these 4 quadrants. For instance, there is a bar here, and in red you have the positive torque, in blue you have the negative torque. Here is a major axis of the galaxy, the projection effect. And of course, we have to know also where is the gas with respect to this quadrant. And the gas in this particular galaxy was here, so it was in the blue region, negative. So when you make an average over a radius, an orbit here, you have this quantification of the momentum that you lose in relative, dl over L, and it is about 1/3 of the angular momentum that you can lose in 1 rotation. So in 3 rotations, all the gas will be driven in the center. So it is not only a way to prove that you are fueling the center, but also how much, with how much rate. And this we have done for some galaxies that we have first high resolution, that HST resolution, 0.1, and also sub-arcsecond resolution with the plateau de Beer to have a CO. We have done this for a while for 20 galaxies with a team called a NUGA team, Nuclei of Galaxies team, with Santiago Estrubello and a lot of people like Eva Schinnerer also here. And our surprise was to find that only 35, that's about 1/3 of the galaxies, were in the fueling phase. All the others were positive torque, so the gas was stored in rings like this. Here you see that 6951, where you have zoom of the center region, there's a bar here, and you see that there is, all the gas is stored in the ring, meaning that you have a positive torque inside the ring and negative torque outside. And it's not fueling, at least. And here you see a little simulations snapshot, 3 snapshots here, and the zoom here, where indeed in the simulation you see the same kind of thing. All the gas is driven to the ring, but after a while, when the gas is making this gas concentration and mass concentration, that you see that progressively you find a nuclear bar inside the ring and you dissolve the big ring to go further to the center. So this embedded structure can indeed solve the problem of fueling. Then the fueling phase is short, but at least you can see that. Of course, there is a lot of star formation also in the ring, so it prevents that all the gas is fueling. So it's 100% scale. And I can show some details here because it's really a good example where, of course, these rings are always pseudo-ring because they are just the ring made from the ILR, but it is the dust lane which are along the bar that are the contact points to the ring. And here you see a little dust, so maybe there is some little bit of gas that we don't see because not enough resolution with CO. But when you look at HCN, a surprise, also with the plateau de Bure. Here, you see that the contour of HCN is the black contours. And there is some HCN in the ring, but there is HCN in the center where you don't see the CO, which was a surprise, meaning that the HCN over CO ratio in the center was larger than 0.4, while it was 0.02 in the ring. So there is something very strange here. We think that it is due to the XDR excitation, because we see that in 1068 also, when you are very close to an AGN, you have an excitation that can have this high density gas excited here. And one thing we saw also, of course, it's not resolved, you see the beam here, but we see the blue and red, and this is like a molecular tori or molecular nuclear ring, and this is not aligned with the major axis of the big galaxy. So you have already a hint that the nuclear disks are decoupled. And in the simulation also, this was done for Hopkins et al., cosmological simulation, but also with zooming. So you can have a large range of scales, and you have example of this embedded structure that I showed already, that edge on or face on. And you see that when you are close to the center, well, you can make nuclear bars and other embedded structure. And when you are very close to the black hole, since it's a Keplerian potential, you have M equal 1. M equal 1 is fostered by the Keplerian potential. While when you are outside the sphere of influence of the black hole, you have more M equal 2, 2 arms and a nuclear bar. Here you see some of the M equal 1. So all these structures, of course, you have warps, you have clumpiness, fragmentation, twist and bending, and you have also, when you arrive at such a small scale that you can have a dynamical friction of only one molecular cloud that can fall in, that you don't need any gravity torque then. You have the time scale for the dynamical friction, which is in R square. So, and of course in 1 over m. So you have to take all this into account to fuel the AGN at a small scale. Now I should show you some example of this. When we went to ALMA at the first cycles, we just look at one of these typical galaxy, a bar here, and with a nuclear ring at ILR. And then we wanted to know what was inside the ILR, to know what is a dynamical mechanism to fuel the AGN. And what we find is a second ring inside. It was not, well, there is a nuclear bar in the near infrared, so in the stars. But in the gas, you see the blue is HST, and in the red orange, it's ALMA. So we have about about the same resolution here than HST. And we see a second ring, which was not obvious here. We think that there is a second ring and the second ILR. And there is also a flow, an outflow that we detected in the minor axis, which is almost the smallest outflow, molecular outflow possible, but it's still sensitive. And the gravity torques show that it is not fueled, and not fueled by a large amount. Here you see the decomposed, well, deprojected gas surface density. The big ring is here and the small ring here at 200 parsec. And you see that, of course, this is an outflow, but here you have positive torque. So the positive torque is to push the gas toward the ring and not to fuel the AGN. And here is only a negative torque outside the ring here. So at 200 parsec, and you have negative and positive, so this is exactly the criterion to form the ring here, and it is exactly what you see. But in another one, for instance, 1566, this is the large-scale view of the galaxy, Seyfert 1, for arcmin. Now we have a field of view of 18 arcsecond with ALMA, so we have a less than 0.5 arcsecond here, 25 parsec resolution. And what we see inside this, we see a nuclear ring. And the nuclear ring was surprisingly also with a spiral, a nuclear spiral, which is trailing. And this was a surprise, trailing. You see the trailing structure in the same sense of winding the small structure. And why is it? There is no outflow at all. In the PV diagram doesn't show any outflow here. But why it was very interesting to see this trailing? Because if you follow the orbits again that I've described at the beginning, you were maybe expecting leading. In fact, because here you have the stellar periodic orbits. I told you that parallel to the bar, which is horizontal here, you have the X1. You are in the referential frame of the bar, so at co-rotation you have no turn here, only this at the co-rotation, and this at the outer limb-blood resonance in the outer parts. And again, if you are inside the ILR is in general at the peak of this curve, omega I minus kappa over 2. If you are inside, you have a curve which is going down now when the gas is coming in. And then it is not leading, it is not in advance, but it is in the reverse sense. So if there is no black hole, so it is in this part of the diagram, you expect a leading. And if it is leading, it is gravity torque is positive and you form a ring and so on. But here, if you have a black hole, you see that all curves will go up, the velocity, the omega, and omega minus kappa over 2 also. So if you are able to enter the sphere of influence of the black hole, then you will see the reverse sign of omega minus kappa over 2, and then you will have a trailing spiral. And this is what happens here. So in fact, the black hole, the presence of the black hole makes the fueling of the AGN. And when you plot exactly the torque map, you have again the 4 quadrants. The blue is negative and the red positive. And you see that the gas, the trailing spiral in the center, in the nucleus, is exactly in the blue one, so it's negative, and you have this negative thing. So we're able to see for the first time that we are in fueling the AGN because there is a black hole. And this, we have now 8 galaxies like that, and we found in 3 cases, so it's almost 30%, but in 3 cases we find this small spiral structure, which is always trailing. Here you see NGC 613, which was already observed with ALMA by Miyamoto et al. And here is the nuclear ring at inner blood resonance here. And they had not enough resolution to see really the structure of the nuclear ring here. And now we have 0.06 arcsecond resolution, so it's really good. We have 5 parsec resolution. And you see clearly that there is a spiral which is trailing. So this appears now clearly. Here you have also kiloparsec size. The velocity field, which is the major axis, is almost horizontal. And zoom here. Here you have only 0.5 second. And the contours are the CO322 intensity of this nuclear spiral, and in the center the color is a continuum. So it's the AGN, which is exactly in the center. And we think that there is a molecular torus or nuclear ring because it is decoupled. You see in HCO+, which is a density tracer, this region, 50 parsec, 0.6 arcsecond, that we have at least a factor 10 pixel in it. And this is exactly the size of this continuum here. And what is interesting is that now the velocity field has a gradient north-south. So it's completely decoupled from the east-west major axis here. So you see that there is a nuclear ring decoupled morphologically, but also morphologically because it's separated here, but also kinematically. So it has not the same. And we will see that it is the rule, in fact. Each time we see this molecular torus, we see a decoupling. And in this galaxy, there is also a small outflow that we see here in the PV diagram, and we see also in the wing of CO322. We are just inside here, it's very, very small. And when we compute the torques, the same way that I described for the other galaxies, indeed we find exactly in the center, in the trailing spiral, we find the negative thing. And of course, it's positive in the filaments. You still are maintaining the ring which is here, and negative in the outer part. So we can explain by the torques exactly the morphology and the decoupling of the nuclear ring. In this galaxy, there was also some other information of the continuum here. You see that the VLA at 4.9 gigahertz show the little jet of the AGN, and it's exactly in this direction that we see the outflow. So it supports the molecular outflow. We had also the iron and the VLA together. So in this direction, there is indeed a support to see that we have the radio mode, that is the radio jet is dragging away the molecular outflow. ISIO is detected in these points, which means that there could be some shocks in the molecular gas. And also, there is star formation, active star formation in the ring, because here you have still some positive torque and negative here. You see the dust lane and the ring, and some people like Bucker et al. Have tried to have the star formation history, in fact, and to know if you had two models here in the ring. Either you have clumps that are forming completely randomly, it's a popcorn model, star formation, or you have gas falling in by the dust lanes, the contact point to the ring, and entering here, making some star formation with some history. And you see in blue, you have the helium-1, which has a potential of ionization which is bigger than the two others, and meaning that you need massive galaxies, young galaxies to ionize. You have the green Bear gamma, and you have the red, the iron, which has a lower potential of ionization. So it's more, you can have an age indicator here, and indeed you see the blue, green, red, which are coherently spaced. So we think that indeed it follows the star formation history. So it's not a popcorn, it's not random, it is coherent.
Sorry, where do I see that? I don't really...
Here you see the blue, the green, and well, it's not as pretty as the little diagram here, but they claim that you see a blue here, a green here, and a red here, and a red here. Here it's redder. It's more orange, it's more green, and it's more blue. So it's blue, green, red, blue, green, red. Maybe. It's not as ideal, I agree with you. Yes, the south is better than the north. Well, it is their claim. So in 1068, in fact, it was the first galaxy where we discovered this molecular torus that we're searching for. You have this galaxy which is in CO322 with ALMA. You have a nice, well-known, it was known well before, this spiral structure, and with a nuclear ring again. And this nuclear ring is in the ILR of the bar. You see that the AGN is not at the center of the ring, and it is frequent. It's even the case in our own galaxy, where the center is not, the nucleus Sagittarius N is not at the center of the ring. Here's the same. The AGN is here, and the ring is there. And also, we find an outflow, and the the AGN jet is impinging in the disk of the galaxy. Here you have a cocoon of what we interpret from the observation. It is a disk edge-on. The ring here, it's not, the AGN is not at the center, and the AGN is not, the accretion disk is not at the same inclination as the disk, so the AGN jet is perpendicular to the accretion disk, and it is sweeping out the gas of the galaxy. That's why there is more coupling than if both were aligned. You will have an AGN jet perpendicular and you have no coupling, so you have no impact of the feedback. But here you have more feedback because there is this random orientation and sweeping the disk. And that's what we see here. And when you have more resolution even, so inside this nuclear ring you see this molecular disk. And now we are at a radius of this molecular torus of 3.5 parsec. So it's inside the insider here, and it becomes to be a bit complex, and that's why I put this scheme of instability that were computed by Papaloiso and Pringle, because these rings are precessing and unstable, and we think that what we see, because we don't see, there is an H2O maser in this galaxy with a large velocity, and we don't find the same velocity. So we think that the nuclear molecular torus is inclined and precessed, because if it was exactly edge-on that we should expect, we will have found the same velocity as the H2O maser, and we don't find it. So, and you see here in contours the continuum. So of course we are also perturbed because the CO is both in an outflow and perpendicular in molecular tori, but at least it's complex. It's not easy to interpret, in fact. And when you look at the dust and optical view, you see that indeed you have a molecular torus which is perpendicular to the line of sight, and you see some polar dust here, which is also seen in other galaxies. So you see how the inclination of the disk is completely different from 1068, which is almost face-on. And since it is a Seyfert 2, it's a prototype of Seyfert 2, you have a molecular torus which obscures completely the AGN. So you have an edge-on torus, and indeed you have a support of this view here, but it is completely random with respect to the inclination of the disk. And no, I think, yes. This has been done by Asmus et al. Out of 150 AGN, they found 10% or a little more than 10%, which have this polar morphology. 1068 is not an exception. There are some like this. You see the green line here, and the torus is perpendicular. So there is also some gas and dust that is dragged out in the outflow due to the AGN jet, and this, the percentage of the observation is instructive to know how much you can have some feedback here. Okay, so we see some also very well contrasted ring. This is a bar galaxies where you have a nuclear ring, and this nuclear ring you see with HST, it is also concentrating all the star formation in this red thing. This is the 10 arcsecond 700 parsec, which is always the 1 kiloparsec ILR. And then when you have more resolution, you see the ILR is here, and you see inside this molecular torus, which looks more edge-on. And we define this torus here at 1 arcsecond. So the contours are again CO322, and the continuum is in the colors. So you see the structure, which is again decoupled. 1365 also is an example of that. You all know this very beautiful bar spiral with this dust lane making this kind of ring here. In the intensity of CO322, you see this structure here, in velocity and in the width. And when you go inside here, you have this little torus, which is almost face-on, with a hole. And when you put the continuum, or the ALMA continuum, here the contours are the CO322, and the ALMA continuum is just in the center of the hole. So it's like a torus with this AGN in the center. You see the intensity and the velocity. So making a summary of the 8 galaxies that we had with high resolution, we find a torus in or nuclear disk, if you want, torus or molecular disk, in 7 out of 8. Only this one, when you look at higher resolution, you don't see a decoupled thing, so we don't see that. But you see how we measure this, the radius of the torus here in parsec, 20 or 10 parsec, the smallest is 1068. And it is not only by morphology, but also by the decoupled kinematic. You have major axis, you have a gradient of velocity, which is not aligned to the gradient of velocity of the whole galaxy. You have the inclination of the torus, which is different from the inclination of the galaxy. So you have really morphology and kinematical decoupling, and that's how we measure. And you see the mass of the torus is a few 10 to the 7, the order of magnitude. Now, there is this galaxy 1672, which is also, again, you see the HST here with a lot of dust, a ring, a nuclear ring at the ILR. It's a barred galaxy and so on. You see very well in radio, which is also a tracer of star formation by the free and synchrotron and Chandra and so on. But this one was very interesting because it has a very intense velocity gradient in the center. Here you see that we are sampling only this ring here inside the slates. So this ring is the big ring here that I showed with the centimeter radio ring. And you see it was almost face on. And now inside you have this decoupled molecular torus, which is really decoupled morphologically and also kinematically because the gradient is not at the same inclination. You see the gradient here and morphology. And when you look at, well, first the velocity gradient here, again in yellow it's the CO contours and the colors at the continuum. You see the velocity, which is non-circular motion again. And for HC and HCO plus, we detect it, but only in the center, so it does not give more information than CO322 for the kinematics decoupling. And, but what I wanted to emphasize here, again, in this small ring, is that with each alpha, we have a gradient of velocity along the major axis, but which is not very high. Here you have, of course, the seeing is 1 arcsecond, so you have a smoothed rotation curve in 2 arcseconds. When you see the ALMA rotation PV diagram, you reach 200 km per second in only 10 parsec. So it's really a large velocity gradient that you have in this nuclear ring. And when you want to explain this with the potential that you get from the old stars, and this we did that we took the near-infrared, we decomposed in a bulge, disk, and so on, but mainly the bulge is doing the most of things, and we find this PV diagram predicted from the simulation. It's not fitting at all, so you need a black hole to fit that, and you see why. Here you have 2 parts of this rotation curve. You have one which is peaked due to the black hole, and you have one which is, again, the disk and the bulge which is continuating. So you have this peak here and this peak here. And this is exactly more fitting. So this means that we are just inside the sphere of influence of the black hole, and we can measure by the kinematics of only the gas the mass of the black hole. And it is very interesting because this kind of low black hole mass is a few 10 to the 7, is very hard to have. You need a very high resolution to have, and I will show you the M sigma relation is very scattered. So we did this for the 8 galaxies. That is, we get the potential from the near-infrared images, we make a gal fit of the bulge. So you see the contribution of the bulge is in red. The disk in green is almost negligible because you are 10 parsec or 50 parsec. So the disk is negligible, the bar also. Maybe sometimes there is a nucleus, maybe a stellar nuclear stars cluster. And finally, the total, when you have an M sigma relation, just to give an idea, the total rotation curve is due to the black hole. So you are indeed, you see the scale is 20, 40 parsec. You are inside this sphere of influence of the black hole. So we are making some simulation of the gas in the potential. We make some particles to simulate an axisymmetric disk. For the moment, we have not done any non-circular motion due to a bar. It will be a second approximation. And we put a disk with asymmetric drift with a Q-term ray called 1, and just to make more realistic. And then we try to fit that with several mass of the black hole. You see that you need at least 5×10⁷ or so. And of course, we can also fit not only the PV diagram, but also the moment of the map, intensity, velocity, moment 1 and moment 2. And what we found is that, of course, we cannot fit the non-circular motion because there is an axisymmetric disk. And of course, we have also removed the part of the smooth disk that we don't see in the observations, because of course we have, if we have no gas in this part, the velocity will be perturbed by the sampling of the space. So here is the model, here is the observations, and the velocity gradient is okay, but the velocity dispersion is hard to model. We think that it is because we don't fill with the observation, we don't fill all the space. Of course, we have not enough resolution to see it, but you must have clamps that don't sample all the volume, while in the model we sample all the volume. So we always find a dispersion higher. And here is, for instance, the modelization of 1365, which were a torus here. So here is a model, and here is the observation. So we find something relatively the best fit for the mass of the black hole. And I compare to this another observations by the Wisdom Project, Onishi, Davis, Bureau, and so on. The groups have done about the same kind of thing, but for bigger galaxies, early type galaxies. Their black holes are of the type of 10⁸ solar masses. And of course, they don't need as much resolution because the black hole is higher mass. The sphere of influence of the black hole is of higher size. So they have only 0.6 arcsecond, while we have 0.06. And you see in this galaxy, for instance, well, it's an adjoint galaxy, but they have a PV diagram. And with a zero mass of the black hole, they have this grayscale which is not fitted, while when they take a 6×10⁸, they fit this grayscale, so they need a black hole. Of course, it's difficult to model here. They have another case here, again at John. This is kind of early type objects again, which big bulge, so big black hole. And you see again with no black hole and 10⁸. And another one which is not quite adjoint, but then there is a hole in the center. And it's very pity, because it's exactly what you want to sample to have the gradient of velocity. So this is less demonstrating, I think. And there is another one, which is 1097, more late type galaxies with a ring also and a nuclear disk, which is seen in CO222, but also in HCN, as you can see here, Onishi et al. With ALMA. And you can also try to fit the grayscale being the ALMA observations, and the contours being their model with a certain mass of the black hole. And this is approximately the best fit here, because here you have a more gradient here that you don't see, and so on. So these are the similar approach that we have done, but with much higher masses. So I plot here a summary of all these masses of black holes obtained with ALMA. The blue ones were from the Wisdom Project with big galaxies and big black holes of 10⁸, with CO line or HCN. And you see that the high masses are less scattered in the M sigma relation, this well-known relation. You have more relation, more correlation, so relation more defined here. And the problem is to know what is really the black hole in this small mass N, and why is it so scattered? In fact, this is a big question. It is possible because there is a pseudo-bulge due to the bar In fact, there are two kinds of bulges. You can have a classical bulge due to the minor mergers or pseudo-bulge, and it's possible that the pseudo-bulge is not a tracer of the accretion of gas as a classical bulge is, so maybe it's not a tracer of the black hole. So anyway, we need to understand what is coming on here and to have more mass of the black hole in this part of low mass and low sigma and low mass of the black hole. So our 6 black hole determination are in red here, and what we see in blue, in cyan and in green are the previous determination from the M sigma or Tully-Fisher relation and so on. So at least we need more statistics, but there is a hope that we can reduce the scatter and understand much better what is the mass of a black hole in these galaxies. So now I come back to the non-alignment of the nuclear disk to the host disk. And this is very interesting, as I mentioned, because you can explain better feedback, better impact of the feedback. I think it's the same in the Milky Way, where the Milky Way you see it at John, and when you look at the center you have a nuclear ring. In orange is the HCN here, and inside it is the ionized gas of the mini spiral here, you recognize. And also in 4258, which is a prototype also known for a long time, where you have normal arms and anomalous arms in blue. In blue it is the radio jet. It is a continuum in a centimeter wavelength, and you see that the jet is in the plane, and each time it encounters an arm it is deflected, so the jet is not straight but it is deflected. So it indeed makes a hole in the disk, and it is true when you make a CO map of this galaxy you find a hole, a canal, a channel. So here you have at least some feedback in fact, what it is. And you can explain why you can have such a feedback in this galaxy. For instance, it's an extreme case where the AGN, which is in blue here, in blue is the VLA emission, so you have the nucleus and the 2 lobes, and it is exactly in the plane of the galaxy. So each time you encounter a cloud here, you have a jet perpendicular, and this was shown in the symphony with the near infrared line, H2 and FE and so on. So at least we understand that we need to have this random orientation to have more feedback. We have also examples recently with the closed AGN reference survey that we are doing here with Bernd Husemann. And one example of this, these AGN are higher energy. It's about 1% Eddington, meaning that the luminosity is 1% the Eddington limit. And here you have a Hadron galaxy. I don't know if you see very well, but there is a green line here, which is the O3 obtained with MUSE. This is very strange. At the beginning we thought it was an outflow, but it's not at all. It's just a gas which is normal velocity. Certainly it has been driven in the halo due to the fountain effect, and then the quasar is just illuminating this gas. So it's a normal velocity, and it's like a cone, O3 cone. But there is, in white here you see the AGN jet. Again, it is maybe impinging on this ring. You have a ring here in CO, in O3 and so on. And we see neatly this, we see this ring, or this wing here in a blue ring, which means that there is a molecular outflow. So each time we have a radio jet, and this was not expected because there is a 1% Eddington. In fact, I recall you the 2 modes of AGN feedback. When you have a large accretion rate, that is a strong AGN, and the luminosity is close to Eddington, then of course you have this radiation pressure. That is exactly the definition of Eddington. It's that you have too much radiation pressure, and then you reject the gas that is feeding you. And the limit here is 1% Eddington. And then you can have a quasar mode, that is a wind, which is more isotropic. And in the second mode, when you are Eddington of 10 to the minus 5, 10 to the minus 9, like in the Milky Way or in 31 and so on, then you can have a radio mode that is only the kinetic energy of the plasma, the radio jet, which is non-thermal and which push and drag the molecular gas. And this is indeed what we observed in the low luminosity AGN. This is due to the corona that you have and not the accretion disk. So we have also another one, which is the consortium that we are observing with Alonso Herrero, which is the GATOS consortium. There is still another ALMA CO322 in this galaxy. You see again this nuclear disk that you see here, which is perpendicular, which is completely different, if I can see. There is a nuclear disk here. And we find also in the velocity some outflow. When we make a cartoon of what we interpret here, we have some nuclear disk in the center and some radio jet. And we can also see the Muse O3, which is in the same direction and which is completely decoupled from the rest. And I emphasize here that the velocities, red and blue, were interpreted by the 3D Barolo model by a radial component, not only a tangential component. And this is interesting because there is always a degeneracy between an outflow and non-circular motion. And we have to be aware that we have to have some other arguments to determine if it is an outflow or a bar or whatever. So in this case, we interpret it as an outflow. There is one case where there was no AGN feedback, and it was 1808. There is in this galaxy a lot of dust lanes perpendicular to the disk, so we know that there is an outflow, but we think that it is a starburst outflow and not an AGN, because at small scale we don't see an outflow. And in small scale, again, we see this nuclear spiral which is trailing. We see it in the continuum also, but no outflow in the center. Here you can see in HCN, HSO+, the dense tracers, you see exactly the same nuclear spiral, and you see the beam is 4 parsec here, so we have defined again the molecular torus, but at this scale there is no outflow at all, while there is already defined for a long time an outflow, a feedback at 100 parsec scale. So it is a starburst feedback like M82 feedback, where you have something which is more an opening angle, which is more vast, but it doesn't come from the AGN. So when you have the resolution, you can distinguish between the supernovae and AGN feedback. So this is, of course, a higher scale when you have not only here the nuclear spiral, but also the ring at Lindblad resonance. At this resolution, you cannot see the trailing spiral in the center. And we have also symphony argument here to know that you don't see any outflow here. Okay, so now in the last minutes that I want to stress here that once you are fueling the AGN, you are also fueling star formation in the ring. I just told you that negative gravity torques can make the gas pile up in rings, and this has been studied by these authors here, and they have Ma et al., and they have found some correlation between the star formation rate and the mass of the ring, except for maybe 1512 and 14.3, the two cases where there is very young star formation. But there is also a correlation between star formation and the ratio of mass of the ring to the galaxy. So sometimes there is a lot of star formation in the ring. And I want to stress also that when you have a bar, you quench the star formation in the bar. In fact, the large velocity and shocks that you have in the dust lane quench the star formation. So in bar galaxies, there is less star formation than in other galaxies, but only all the star formation is focused in the ring, and then you see it very nicely. And for the Milky Way, it's about the same thing. Krumholz et al. Have just make some model of this and shown that there is some burst of star formation in this ring, and you can see here the Koenig-Schmidt diagram where you have the surface density of stars and surface density of gas, and you are in between these two dashed lines. The first one is low star formation, so 2 gigayear depletion timescale, and the up is a starburst with 0.2 gigayear depletion timescale. So you are oscillating here between the burst and normal star formation, and this is what you find here. In the Milky Way, you have this nuclear ring, which can be analogous to all what we have seen before, the ILR. It is a 100 parsec scale. We see it in Herschel. It is not exactly in a plane. It is twisted and corrugated, but there is a ring. And when you look, the ring, of course, in velocity, it has a parallelogram, so non-circular motion, which is obvious. And as you see, it is not centered. The zero is here, and it is more 3/4 of the gas is in one side, so it's like 1068, in fact. And we have already focused on this inclination. And to interpret how you can make this non-alignment, I just want to mention this simulation by Renaud et al. Of the Milky Way. It's a Milky Way-like galaxy. You have some snapshot here, and you see that at some time it becomes, the nuclear ring becomes unstable to star formation. So you have this gas here making some clumps and star formation, and then there is some feedback, some fountain effect, and then it comes back, and comes back with any orientation. And the bottom line is that you have a polar ring. In fact, you see something perpendicular, which is rather stable here. Of course, you have an angular momentum, which is completely different. When you put here the face-on view, you have this perpendicular structure, and the edge-on view, you see the polar ring face-on, which is this, and this is edge-on view. And this is due only to the fact that when you are at 10 parsec scale, it's only, it needs only one cloud to collide and accrete to digest the angular momentum, and you can change the orientation of the total when it has gathered all the angular momentum, which is different. So it's very easy to make this random orientation when you are in the nuclear ring, which is a time scale of 10 million years. So in summary, I will say that we are now understanding better the mechanism of fueling. The bar drives gas to 100 parsec scale, make maybe sometimes a ring for a while, transiently, 100 parsec scale, and then after a while there is a large mass concentration, and you can decouple to form an embedded structure, either nuclear bar or nuclear spirals. You are at the 110 parsec scale, so you can have also clamps, warps, and we've seen embedded structure of M=1. And then you are fueling your AGN, and you can have the feedback outflows that are seen in molecular gas. And you can have strong coupling because of this misalignment that is due to the fact that you can accrete in a gas with different angular momentum. So, okay, thank you very much.
So, many thanks, Francoise, for this very nice and very detailed overview of how gas flows to the galactic center, can fuel the active galactic nuclei, and can explain many other of the observed features that we see in our Milky Way, but also in nearby galaxies. So I see a few hands up. Let me first make more light. And then I start with Mattia and then with Dietrich. Wait, microphone.
So I was wondering, have you tested the method that you use to derive the inflow and outflow using some simulations? For example, you pretend the simulation is the observations, and you apply your method, and you check that it corresponds to the actual inflow that you can measure.
Yes,
because
yes.
I'm asking because there are two assumptions in the method which are not obvious to me. So one is that the gas density is in a approximate steady state. It doesn't change with time, the density distribution. And the other is that the CO or the tracer that you are using is a good tracer for the mass of the gas.
Okay, so there are several questions here. First, do we check that the outflow is corresponding in the simulation and the observations? I think we have the energetic is right. Of course, you have orders of magnitude to know the outflow rate. You have to make an assumption. M dot, you have N dot, you have the time scale at which this outflowing and so on. So I don't claim that we have a factor 2s. but at least the order of magnitude is good, that when you make a simulation of outflow, and many people have done this simulation, it fits from the energetics and the... Yes, for the torques, so inside, yes. It's not the outflow, it's inflow. And outside rotation, then the outflow, yes? Yes, and this, exactly, when you make simulation of inflow in a bar, numerical and body simulation, we find the same.
Yes, but have you tested in detail that the method works? Like, you know the mass distribution, you do, in the simulation, you make mock observation. The torques on the gas, and you find that.
Yes, in fact, the only confrontation from the simulation observation is exactly the near-infrared map that we have done to have the potential. We need to have the strength of the bar to know the strength of the torque, and then to know where is the gas, to have the phase shift between the gas and the potential to have the torque. And then we have computed that in 2 or 3 rotations, the gas is going to the center or to the outer parts. If you're outside rotation, you get to the outer part. So it fits with the observation, yeah, and the simulation, yeah. But of course, you can find different bar strength and so on, so you can have twice shorter time if you have a strong bar. So it always fits.
So, Dietrich?
I have a question connecting the final part of your talk to the beginning, which is that you showed at the end, in, for instance, the MSLM simulation, that sort of the real circumnuclear streams are not nice and tidy as the rings that you show in the observations. And in the Milky Way too, we know that the central, the circumnuclear stream doesn't nicely close on itself. It sort of wraps and sloshes and so on. How concerned are you about effects like that, where things like eccentricity and non-circular motion might play a role? How worried are you about that when you constrain enclosed mass profiles, black hole masses, and so on?
Yes, yes. In fact, in the galaxy that we fit, there was only 6 galaxies where we fit the black hole. It was less lopsided. We forgot about the lopsided thing. So in 1672, that was this. It was symmetric. It was not lopsided at 5 parsec. So we have confidence by that. But I agree with you that if we go at higher resolution and we find 1 parsec, then we have an error bar. So our mass of the black hole have big error bars.
So it's within the error bars?
Yes. But we try to find those who are less lopsided. But it is the best we can do.
Sebastian.
Thank you, very nice talk. I have a question. So you mentioned about the kinetic feedback in the AGN. So there are some people who claim that if you assume that this blunt force mechanism is responsible for that, whenever you have counter-rotating accretion, this process is much more efficient. So do you think that fragmentation due to cell gravity in very massive accretion disk might play a role in inducing this counter-rotating accretion?
I don't know, in fact. I must say I don't know. For the moment, what we have found in the observation and in the simulation, they were all rotating in the same sense. There was no counter-rotation. But I agree with you. It is a possibility that we have not yet either observed or studied in the simulation. So I cannot tell more than that.
So, next question, Kees Dullemont.
At some point toward the beginning of the talk, you mentioned that in the Keplerian part of the potential, you would have m=1 spirals, yes, and further out you have m=2 spirals. Maybe I just didn't follow it. Why is there a reason?
Yes, because it's the shape of the potential. The potential is Keplerian.
Yeah.
And this, when you look at 1/r potential, it fosters the m=1. I can put in the equation, but when you have a potential which is not like this, but distributed symmetrically and so on, it's m=2. but I have not the power to write the equation for that. But it's well known. It's well known, and Frank Schuh, for instance, has made this lopsided thing. This was m equal 1, and we simulate and we find also m equal 1 when we have this potential in Keplerian thing.
Okay.
And this Keplerian thing also explains why we have some AGN which are not at the center, because m equal 1 is asymmetrically, is lopsided. When m equal 2, you have you force the symmetry.
I see no more questions.